Hi guys! In this video we're going to be looking at Introduction to the Photoelectric Effect, the gold leaf electroscope, key observations from the photoelectric effect, and we're going to finish with a summary. So first of all we're going to introduce the idea of the photoelectric effect and actually understand what it is. Metals contain conduction electrons. So here we have a metal rod, and if we take a look at its structure in a bit more detail here, we can see that the metal rod is made up of these conduction electrons and also positive ions. These conduction electrons are delocalized, meaning they are free to move in the metal. So our electrons here are delocalized, which means that they're free to move. So for example, this one might move here, this might move through here. Essentially, the electrons aren't bound to the ions, they're free to move around the metal. When Heinrich Hertz shone UV radiation onto zinc, he observed that electrons were emitted from its surface. So here we have UV radiation, which is incident on some zinc metal. So this here is our zinc rod. And what Hertz observed was that electrons were emitted. So this metal rod emitted electrons when UV light was incident on it. This is known as the photoelectric effect. So the photoelectric effect is when we shine light on a piece of metal like this, a metal surface, and when the light is shone on the surface, electrons are emitted. And in this case, the metal was zinc metal. The electrons emitted are called photoelectrons. So when our UV light is shone on our zinc metal, these electrons that were observed to be emitted were called photoelectrons. And this is because they're electrons that are emitted due to the photoelectric effect. So that's how they get their name. So now we're going to see how the gold leaf electroscope enables us to observe the photoelectric effect. The photoelectric effect can be observed with a gold leaf electroscope. So this is the gold leaf electroscope that we can use. And we can see we have this metal plate on the top. This here is an insulator. This is our gold leaf. This is a metal stem. And it's all placed in a case. So that's the gold leaf electroscope that we can use. If we connect the top metal plate to the negative electrode of a power supply, the electroscope will become charged. So the top metal plate is connected to a negative electrode. And since it's connected to the negative electrode, it becomes negatively charged. So we have a negative charge built up on the top metal plate. Excess electrons from the plate will flow down the stem. So we've said we've got a build-up of negative charge on the plate. However, some electrons are going to flow down the stem. So that's what we've got showing here. These electrons are going to go down the metal stem. And the metal stem we can see is inside an insulator, so charge doesn't escape. These electrons are then deposited in the stem and the gold leaf, extending the negative charge. So now not only is the top metal plate charged, this charge now extends all the way down the metal stem and also down the gold leaf. Both the stem and the gold leaf have the same negative charge, so they will repel each other and the leaf is lifted away from the stem. So now that our negative charge has extended down to the metal stem and the gold leaf, we know that two negative charges repel each other. So the gold leaf and the stem are going to be repelled. And as the two negative charges repel, the gold leaf is going to move up. If the negatively charged metal plate is made of zinc and we shine UV light onto it, then the gold leaf falls. So now we're going to say that this metal plate is made of zinc, and when we shine UV light, we can see that the gold leaf falls back down. But why does this happen? Well, this is due to the photoelectric effect causing electrons to be emitted from the zinc surface. So when we shine the UV radiation onto the zinc plate, we get the photoelectric effect that we've just introduced. So we shine UV radiation onto the plate and then photoelectrons are emitted. And then as the electrons are emitted from the top metal plate, the electrons flow upwards from the metal stem and the gold leaf, so eventually they become neutral again and no longer repel each other. So once the electrons from the metal plate have been emitted, electrons move up from the gold leaf and from the metal stem. So we can see that here, these electrons are moving up and they're emitted. And as the electrons are emitted, these two are now neutrally charged again, which is why the gold leaf falls, because it's no longer repelled. Now we're going to look at some of the key observations from the photoelectric effect. There were 3 key observations that scientists made from the photoelectric effect. So we've said that the photoelectric effect is when we shine some form of electromagnetic radiation, in this case UV radiation, onto a metal surface. In this case we're looking at zinc, and when this radiation is incident on this surface, electrons are emitted and we call these photoelectrons. So the first thing observed is that for a given metal, no photoelectrons are emitted if the radiation has a frequency below a certain value. So for example, if light of a lower frequency was incident on this metal, and light of a higher frequency above this certain value, that photoelectrons are emitted, and then if light of a higher frequency was incident upon this metal surface, it was observed that if this light of a higher frequency was above a certain value, electrons were emitted. So these electrons are free to escape from the metal. However, here, where we have a lower frequency, electrons were not emitted. So essentially what was observed was that the frequency of the radiation determined whether electrons were emitted or not. The minimum frequency the metal needs to emit an electron is called the threshold frequency. So if we have radiation incident on the surface with a threshold frequency, then it was observed that the first electron would be emitted. So once we reach this threshold frequency, that's when electrons start to be emitted. Below the threshold frequency, no matter what the intensity, no electrons will be released from the surface. So if the incident radiation is below this frequency, no electrons are emitted. So for example, we might have incident radiation of a low intensity, and this is below the threshold frequency, and it was observed that no electrons were emitted. However, if we have radiation of the same frequency but of a higher intensity, so this is still below the threshold frequency, but now the radiation is of a higher intensity, it was observed that still no electrons were emitted. So whether or not electrons were emitted solely depended on the frequency of the incident radiation. The second observation is that the photoelectrons emitted have a variety of kinetic energy values, ranging from 0 to a maximum value. So again, we have our incident radiation. And when electrons were emitted, there were a range of values. So for example, this electron here might have the maximum kinetic energy value. This electron here might have a kinetic energy of 0. And the other electrons in between have other values of kinetic energy that range between these two. So there was a range of kinetic energy values. And along with this, it was observed that the maximum value of electron kinetic energy increases as the frequency of the radiation increases. So here we might have some incident radiation of a low frequency, and it would be observed that this electron would have a low maximum kinetic energy value. However, if we have a higher frequency incident on the surface, it was observed that this electron emitted would have a higher maximum kinetic energy. So now we have a high maximum kinetic energy. So depending on the size of the frequency that's incident on the metal surface, the maximum kinetic energy values of the electrons emitted would vary. So a higher frequency would mean a higher maximum kinetic energy value. And leading on from this idea of the maximum kinetic energy, the maximum value of electron kinetic energy is also unaffected by the intensity of the incident radiation. So say now the frequency is kept the same, but we have incident radiation of different intensity. So here we have a low intensity, and here we have a higher intensity, but they both have the same frequency. It was observed that even though these two radiations have the same frequency but different intensities, the kinetic energy of the electrons emitted was the same. So they have the same kinetic energy. And the final observation made is that the greater the intensity of the radiation, the more photoelectrons emitted per second. So again, we have radiation of the same frequency but different intensities. So these two have the same frequency, but this radiation here has a lower intensity. So it was observed for radiation of the same frequency but a lower intensity, fewer photoelectrons were emitted. Whereas here we can see we have the same frequency but a higher intensity, and more electrons were emitted. And in fact, the number of photoelectrons emitted per second is proportional to the intensity of the radiation. So the intensity I was proportional to the number of photoelectrons emitted. So that was our third and final observation.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face, and together, let's make A-level physics a walk in the park.